announce yourself.
The Wayfinders of Rowan Cabarrus Community College.
If you have the PowerPoint before us, the first slide is the one with the Rowan Cabarrus Community College on it. We are the Wayfinders from Rowan Cabarrus Community College. Next slide, CDR review outline. This is just a general overview of everything we're going to cover during our presentation. We're going to talk about the minimum requirements of the payload, making sure how we're going to test and make sure that we're following the guidelines, our educational outreach, and then our plan moving forward alongside with our various budgets such as mass and finances. Next slide, the Wayfinders. This is our collection of 10 students plus our faculty. The image on the left is actually a logo that was graciously designed as part of an outreach competition we did by a student at RCCC. Next slide, group organization. And so we decided to divide our team into 6 categories. We sat down, we met, we decided what are the areas that each of us would like to work within for part of the team, and we designed little teams that come up with their own deadlines as part of the greater whole deadlines and work back and forth with the other teams. Because 10 students can be difficult to all meet at the same time sometimes. Next slide, team facilities. So these are a couple of the spaces that RCC has allowed us to work within for part of our project, such as chemistry lab, electronics labs. We also have the use of additive manufacturing lab and CAD software.
Okay.
Next slide, concept and operations.
Hello, sir. My name is Isaac Mayo. I'm talking about the concept of operations. So as you know, we'll have our payload. Initially, we're going to have our checklist to make sure everything inside the payload is good to go. And we will attach our payload to the connector ring and the parachute into the balloon. And we'll launch our balloon, and depending on the winds and the projections of the software will depend upon how much we fill the balloon. The balloon will approximately ascend to 90 to 100,000 feet. The balloon will burst at some point and then free fall in a controlled descent and land. And we will follow or monitor the direction that the balloon goes to, and we will recover the balloon and the payload.
Hi, I'm Kirsten. I'm going to be talking about the minimum/required payload. So what we have here is our sensor package, and we're using the Arduino, the Adafruit Adalogger MO. And as far as our sensors go, we have the accelerometer, the temperature, the barometric pressure, and the altitude sensors, and they're all coded using the Arduino. And we also have the micro SD card. And for our payload release, we're using the Nitron wire, and if there's anybody who'd like to chime in on how that works.
So the different wire has power that goes in, and Aaron will control the software or a number that goes to it, and it will give it a certain amount of current, and then the wire will heat up, and the payload pressure will cause the wire to burn, and the payload will fall down. As you saw in our video from last year, when the payload was stuck up in the tree, we were able to actually get it down without climbing up the tree.
And to make
That was good.
to make sure that nothing could accidentally release our payload while it's in flight, we're of course using separate codes for each of our release wires that need to be put in multiple times, as well as a security feature to drastically reduce the possibility of even one wire being released during flight.
Yeah, like a redundant system, exactly as Ryan was saying. That way, if something happens for some reason, the power won't go to all 4 wires and release the payload. It would only release it from one corner rather than all 4 corners.
Next slide. So we have more about the minimum and required payload, and one thing that I've been working on has been with the Raspberry Pi Zero and the camera module, because that's what we're using as a camera this year. And so the idea is that using a Python script, we will tell the camera to start or stop recording based on any trigger that the Arduino will send it through one of the pins. And specifically, it will turn on based on either temperature or barometric pressure. And the reason why you have to have 2 is, just in case one fails, that it would definitely turn on or off for certain. And we also have the GoPro Hero that was used last year as well with the built-in time-lapse feature.
Next slide.
Okay.
I'm Kyle, and this year we are redesigning our own payload release board to reduce weight.
What process are you using, stuff like that?
M0.
Okay.
Also for on a required payload, we are using a 70 centimeter beeline radio transmitter and a 2 meter
Gotcha.
beeline GPS tracker. We're going to use sensors, a microcontroller, camera, and tracker to test each component individually in the data collection and operation. We're going to test all the components together to ensure compatibility, power supply, and good data recording. And after testing, we're going to solder them in place for preparation for the installation into the payload. Next slide.
Okay.
All right, so our individual payload will include a Geiger counter, a particulate matter 2.5 sensor, and an ozone sensor. So we'll be testing these components the same way as we did last year. We'll put them in a freezer and test these components. We also have already tested the power to them, and we've tested the Geiger counter out. Kyle, he's already got the Geiger counter to where it is working, and it's working with all the power supply that we're using. So one of the reasons we're using the Geiger counter is we want to see the change of rate as the balloon raises in altitude. And we fully expect that the radiation will go, or that the radiation count will be higher in the higher atmosphere than it is on ground level. And we also expect the air quality during the ascent to improve, and the O3 sensor, the ozone, to actually increase. So we're really unsure exactly what will happen, but these are some of the sensors that we have in our payload and some of the different scientific experiments that we're looking forward to completing. Next slide. So this next slide is our payload components. You can see the far left with the two bolts sticking out of it. Those are the actual bolts that go for our payload mechanism release, and we're actually going to put a little bit smaller bolts in there for weight reduction, but that's the mechanism release. The nichrome wire will go in between those, and then it'll receive its power, and then that will burn up. Also, we are using, fewer screws for that as well. And the wiring that we had last year, we had more bulkier wire, as you can see in that. We're using a little bit thinner wire because after doing some calculations, we don't need wire that thick a gauge to complete with the current that we need. So we'll be able to save weight that way as well. And then you can see that we have a couple of antenna sensors that are in the center section. And then our 3 AA battery power pack, which this year we're using lighter batteries as well in our power pack. And then we have a big GoPro power pack to the right that the small USB wire is sitting on top of, and then our 2 GoPros, and right below that another battery pack that we'll be using to power other components, and another little camera, and those are our payload components. And next slide.
Okay, my name is Brad. So what we decided to do this year is redesign our payload enclosure compared to previous years, which we had a more cube-like foam cooler. So this year we decided just to mold our own and make our own enclosure. So we're using a 2-pound polyurethane foam to actually do this. The reason we're reducing all the weight everywhere else is this is actually going to add a little bit, but not as much. So we're going to be able to actually control weight distribution with this shape as well. We're going to allow it to be customizable with shelving. And you see the comb there at the bottom. That can also help to prevent this enclosure actually getting stuck in trees. So the stability goes back to the weight distribution. We're just going to try to focus the weight towards the center of our enclosure. And as I mentioned, it's fully customizable versus previous year coolers. And also we're going to reduce weight. So really last year's coolers we had just the components kind of everywhere. This time we can actually specialize. We put it wherever we like. Yeah, center mass as well.
No squirrels nest inside there.
Yeah, exactly. That's basically it. So I think we're gonna go to the next slide.
My name is Alec. So this is the payload mask budget. This is subject to change. We have already kind of cut down on some mass from the mechanism. We're using 3 connector points as opposed to 4 from last year, so we've cut down the weight on that. The total right now is about roughly 1,200 grams, which is 2.69 pounds, but it's again rough, subject to change. So next slide. So this is our calculated battery run time, and so we'll be good on our run times. So next slide. And our FAR compliance, so like I said before, we're at about 2.69 pounds, which is roughly about 1,200 grams. We are well below the FAR compliance total mass. Our weight size ratio is right now less than 0.6 ounces per square inch, so we're good on that. And we are using 30-pound test kite string, and the compliance design is for 50 pounds, so we're below on that too. So next slide.
Hello, this is Logan. We are going to be testing our balloon off a 3-story building at RCCC with a dummy load, and we are going to be using 3 40 to 60 foot shroud lines between our payload and the parachute, with as was stated before, a 30-pound test kite string, which is below the 50-pound. And the parachute is actually 1 meter in diameter, so that meets the requirements also. Next slide.
Hi, I'm Lily. I'm going to be talking about the educational outreach. So we had this fine art logo design competition held in the school-wide, and we ran a student-led graphic design contest from November to January. And applicants, they have to go on our social media through a link to apply for the logo design contest, and we'll give them $25 for a prize. Whoever wins the competition. Next slide. And we had this VEX robotic competition, and whoever went to that competition can explain what happened that day.
Yeah, so some of our, like last year, we did an outreach program at the VEX robotic competition at J.M. Robinson High School, and we did that as well this year. And you know, all those students there are into science and STEM-related fields, and many students came by and asked us what we were doing and about our payload, and even more of their parents actually talked to us. So we were able to get the information out about the competition for the state to people who are competing in the VEX robotics competition from multiple schools. So not only did it help out to help recruit some students in our area, it helped to get the word out to other areas that they can apply at the schools that they're going to be going to be on the high altitude balloon team.
And also at RCCC STEM open house, this event is going to be held in April 2nd and 3rd. And we're going to be interacting with 500 plus community members and then perform a test launch weather permitting.
Hello, my name is Ryu Pitch, and I'm just going to go over the budget that we had. I'm not going to read all of it as it's pretty lengthy, but I'll sum it up for you. Basically, we got $1,500, and as of today, we have $944.67 to this day. But anyway, we calculated it and managed it very well, as that amount is also subject to change, as it could be going to stability or anything else we might need, so money is not a problem for us.
Next slide. The project plan. So this is just a list of the hard deadlines that we set as our team for deliverables involving the competition. To review the feedback that you've given us, to prepare rough drafts for stuff such as the flight readiness, or the, if you go to the next slide, such as the final report.
Sure.
And next slide, This should be the final slide. It says, and thank you for your time.